Okay. Hi everybody. In this module, we're going to look at the equivalent discrete time models of continuous time system with delays. So just to recap what we've done in the previous module, we looked at how to get the representation of the discrete time system, getting the transfer function, the pulse transfer function, y of z over u of z. We can do this in the frequency domain by taking 1 minus z to -1, the z transform of gp of s divided by s. And in the previous module, we looked at how to do it in the time domain. If we have the state space representation, so this is our plant here, and we have the state space representation that relates the output y of t to the input u of t, or u bar of t. And if I want to get the state space representation that relates y of k to u of k, then I can get it using the expressions that I have here. A is equal to phi AC multiplied by t, where AC is the continuous time, which is equal to e to AC multiplied by t. B is going to equal the integration from 0 to t e to AC tau d tau. And the C matrix is the same. C is the same as C of the continuous time. D is the same as that of the continuous time. Now what we're going to do is we're going to consider what happens if we have a system that has a delay, that has a time delay. Consider how the representation is altered if the plant, the continuous time plant, GP of S, contains pure time delay. And let's say that time delay is T sub D, time delay. And in order to get the new representation, we're going to be introducing a new transform, not a brand new transform, but we're going to take the Z transform and we're going to modify it. And therefore, we're going to be introducing the modified Z transform. So this is going to be the topic of this module, the modified Z transform. Okay, so let's look at, first before we look at the system, let's look at a signal that is delayed. So let's consider a signal or a time function E of t that is delayed by an amount of time equal to delta t, where t is the sample period. And delta is a positive fraction. And this fraction is between 0 and less than or equal to 1. So what that means, if I look at the signal E of t, so let's look at the signal before the delay. So the signal, we have a signal E of t. Now this signal, continuous time signal, I could be sampling this signal every t seconds. So there is a 0, this is t, this is 2t. I can take these samples and then I can calculate the discrete the Z transform from these samples and get the Z transform of the signal. Now what happens if I take this signal and I delay it? So now my signal, I'm just gonna do shift it to the right, and it's gonna look like this. Now I'm still sampling at 0, at t seconds, at 2t seconds, etc. But now when I sample the signal at t, I'm not getting this value here, but rather I'm gonna be getting the value here. Now if I define this as this time here as m multiplied by t, and then I'm going to define this time here as delta multiplied by t. So the signal is delayed by delta multiplied by t. You're going to notice here that this value here that I'm going to take at t seconds corresponds to whatever value the signal is going to be here at m multiplied by t. Together? Actually, let me, just to make it easier probably to understand, let me delete this and copy the other one and just shift it. If I can. Going once, going twice. Okay, doesn't want me to delay it. Okay. So this signal was going all the way like this. So again, this signal is the same as this signal. We shifted this signal by delta t. Okay. So let's see how we can get the Z transform of this signal. Let me redraw this. So I'm gonna do is I'm gonna take this it's not allowing me. Nevertheless, we'll replot it. So this value was here. So now it's delayed like this. And the signal is going like this. This time we said is equal to delta multiplied by t. And this time we're gonna call it m multiplied by t. Okay. So again, when I sample this signal at t, I'm gonna be getting this value here, which corresponds to e of at m multiplied by t. So if I were to plot the yellow, when I take this sample here, this corresponds to this time here, which corresponds to this time here. Okay. We'll come back to it if we need it. So therefore, what we want to do is we want to get the Z transform of the signal E of t that is delayed. Now we know the Z transform of E of t is equal to the summation from n equals 0 to infinity E of n multiplied by t z to negative n, and this is E of z. Now we need to determine the Z transform of the signal E of t minus delta multiplied by t, the signal that was delayed. And this is going to equal to the summation from n equal 1 to infinity E of n multiplied by t minus delta multiplied by t z to negative n. Now this we're going to define as E of z E of z comma delta. So again, we're taking these samples. These samples are going to occur at E of n t minus delta t multiplied by z to negative n, which is going to equal to E of z comma delta. Now this E of z comma delta, we're going to define it as the delayed z transform. The delayed z transform. And of course, notice here, we did not consider n equal to 0. We do not consider n equal to 0. In this summation, we started with n equal to 1. And that is because we assume that E of t is equal to 0 when t is less than 0. So if that is the case, if E of t is equal to 0 when t is less than 0, even if I start with n equal to 0 here, I'm going to get E of negative delta t. E of negative delta t is going to be 0 because E of t is equal to 0 when t is less than 0. So therefore, I can just start from n equal to 1. Now, we're going to define the modified z transform is defined as E of z. I'm trying to stay consistent with how I plot the z, how I draw the z. E of zm is equal to E of z comma delta when delta is equal to 1 minus m. So therefore, we can notice that when delta is equal to 1, it means we are delaying a whole sampling period. This corresponds to m equal to 0. So if I go back to the graph that I did here, if delta is equal to 1, it means this delay is going to go all the way, m is going to equal to 0. M plus delta is equal to 1. M plus delta is equal to 1. So if I delay the signal by delta, the time from the delayed signal to the time I take the sample is defined as m multiplied by t. So this time here, I don't know if the graph is clear or we have to redraw it. This time is m multiplied by t. This time here is delta multiplied by t. Together, m multiplied by t plus delta multiplied by t is equal to t. M plus delta is equal to a 1. Okay. So therefore, since we defined the delayed z transform is given by E of z comma delta equal to z of E of t minus delta multiplied by t, and this is gonna equal to z of, what is the Laplace transform of E of t minus delta s, is gonna equal to E of s multiplied by e to negative delta multiplied by t multiplied by s. Now if I know the z if I want to take the z transform of E of s e to negative delta ts, I can do this by taking E of S, e to negative delta ts star, and replacing e to st with z. Therefore, the modified z transform can be expressed as, let's start a new page. We can express the modified z transform as e of z comma m equal to e of z comma delta, where delta is equal to 1 minus m, which is going to equal to e of s e to negative 1 minus m ts star, and e to st is equal to z. Let's call this equation star. Now this is going to equal to e to negative t multiplied by s multiplied by e of s e to m multiplied by t multiplied by s. And this is a star, and we are replacing e to ts with z. Okay. Now looking at this expression, we can use the fact that if I have e to negative t multiplied by s multiplied by any function f of s, the star, this is equal to e to negative t multiplied by s multiplied by f of s, the star. And therefore we can rewrite the expression above as the following: e of z comma m is equal to e to negative t multiplied by s multiplied by e of s e to m multiplied by t multiplied by s star, and e to ts is equal to z. And this is going to equal to, if I'm replacing e to, let's keep this consistent, I write it ts there, ts, if I replace e to ts with z, I'm going to get z to negative 1 multiplied by e of s multiplied by e to m multiplied by t multiplied by s star, and e to ts is equal to z. Okay, now how do we obtain this? We're going to do something similar to how we obtained the pulse transfer function. We're going to use the calculus of residue, and we can show that this expression e of z comma m is going to equal to z to negative 1 multiplied by the summation, the poles of e of lambda multiplied the summation of the residue ci associated with pole lambda I of e of lambda multiplied by e to m multiplied by t multiplied by lambda divided by 1 minus e to negative t multiplied by s minus lambda, and we replace e to st with z. So therefore e of z comma m is going to equal to z to negative 1, the summation over the poles of e of lambda, and we're going to take the residue ci associated with pole lambda I of E of lambda e to m t lambda I divided by 1 minus z to negative 1 e to t lambda I. And here m is between 0, greater than or equal to 0, and less than 1. And of course this is a strict inequality. And in the case of no pure time delay, if there is no pure time delay, this means delta is equal to 0 and m is equal to 1. Now, if in this case, E of z comma m is not equal to E of z. Why? Because when we factor out E of ts here, we did this, we did it here, we did it with the assumption that m is not equal to 1. Does that make sense? So when we took here this e to negative t multiplied by s, we assumed m is not equal to 1. If m is equal to 1, this is going to cancel. We're not going to be able to take this factor. So the point is m is less than 1 and greater than or equal to 0. M is equal to 1, we cannot use this calculation. This derivation will not be valid. This is valid only when m is between 0, greater than or equal to 0, and less than 1. If m were equal to 1, then this is gonna make this derivation invalid, because when we took e to negative ts here, we assumed m is not equal to 1. If m is equal to 1, this is going to cancel. There is no e to negative ts to take out as a factor. I hope this is clear. Okay. So let's take an example and see how we apply this calculation, how we do this calculation of the modified Z transform, and after that we're going to see how we apply it to a system. So now we're considering just a signal that is delayed. So as an example, we're going to compute the modified Z transform of the continuous time signal and this signal is e of t minus 0.3 multiplied by t equal to 2e to negative t minus 0.3 multiplied by t this is the unit step function, t minus 0.3 multiplied by t. So I have a signal e of t. What is e of t? Without the delay, e of t is equal to 2 e to negative t multiplied by u0 of t. I delayed it by 0.3t. So therefore, in this case, delta is equal to 0.3, and we are given t, the sampling period, is equal to 1 second. Okay. So what we want to do is we're going to calculate the modified Z transform. So we're going to start with E of t. E of t has Laplace transform that is 2 over s plus 1. Therefore, E of lambda is equal to 2 divided by lambda plus 1. Again, this E of lambda is coming from E of s. E of s is equal to 2 over s plus 1, and this is coming from this signal here. Okay, so in this case, we have a single pole. So let's continue here. We have a single pole at, or that is lambda 1 equal to negative 1, and the residue C1 that is equal to 2. So this is the pole, this is the residue. So therefore we can use the residue method E of Z comma M, where M is equal to 1 minus delta, and delta is equal to 0.3, therefore 1 minus 0.3 is going to equal to 0.7. This is going to equal, according to the formula, and let me redo this. This is going to equal to Z to negative 1 multiplied by the residue C1 E to M multiplied by T multiplied by lambda 1 divided by 1 minus Z to negative 1 E to T multiplied by lambda 1. Now in this case we have only one pole, so there is no summation. And in here we know M is equal to 0.7, C1 is equal to 2, the residue, lambda 1 is equal to negative 1, the pole, and T is given equal to 1. So if I plug in these values, I'm going to get Z to negative 1, 2, E to negative 0.7 divided by 1 minus Z to negative 1, E to negative 1. T multiplied by lambda 1 is going to give me negative 1. So therefore, we can simplify this, and E of Z comma M, when M is equal to 0.7, this is going to equal to 2 multiplied by E to negative 0.7 divided by, I can multiply numerator denominator by Z, divided by Z minus E to negative 1. And this is the result that we want. This is the modified Z transform. Together? So we calculated the Z transform of this signal that we delayed by 0.3 multiplied by T. Okay. So this is what happens when we delay a signal. Now what we want to do is we need to calculate the pulse transfer function. Calculation of pulse transfer function G of Z for the case when GP of S has pure time delay. What does that mean? So let's look, let's consider that we have GP of S that is represented as the following. GP of S is equal to Y of S divided by U of S and it is given by Bm S to M all the way to B0 divided by S to N plus AN minus 1, S to N minus 1 all the way to A0. Now this is what we've been seeing, what we've been dealing with all along. Now the new thing that we're going to add is we're going to have a delay, e to negative TD multiplied by S. And therefore, I'm going to write this as GP, no delay, of S multiplied by e to negative TD multiplied by S. So what happens if the transfer function that you're dealing with, that you're trying to design the controller for, has a delay? So whether it is you're trying to, for instance, one obvious example, if you have a pipe where there is a liquid that is going to pass through this pipe, and if you were to pour the liquid here, it's going to take a time to arrive at the end. Or if it is a circuit that has some delays in its operation, or if it's a mechanical system, we need to be able to modify we need to be able to represent that delay and model it so we can account for it. So in this case, we're going to express the time delay TD as the following. TD is going to equal to K multiplied by T plus delta multiplied by T. So depending on the time delay that we have, the time delay might be greater than T. So if it is greater than T, we'll take the T part together and we'll take the fraction of the T as separate. So in this case, T is the sample period and K is equal to a positive integer and delta is a positive fraction. And therefore delta is delta is greater than 0 and less than or equal to a 1. Now this K here is should not be confused with the sequence index. Don't confuse with sequence index. There's so much math that we're running out of simples to use. Okay, so again, we're taking the delay. We're going to represent it as an integer multiplied by T plus a fraction multiplied by T. Therefore, I can take GP of S and I can represent it as GP with no delay of S multiplied by E. I'm going to replace TD with K multiplied by T plus delta T multiplied by S. So I just taken the TD replaced with its value. Now I can write this as GP 0 of S e to negative K multiplied by T multiplied by S multiplied by E to negative delta multiplied by T multiplied by S. Now what we're going to do is we're going to calculate the pulse transfer function. What I want to calculate is G of Z. Pulse transfer function. This is going to equal to 1 minus Z to negative 1 multiplied by the Z transform of GP of S divided by S. And this is going to equal to 1 minus Z to negative 1 Z transform of E to negative K multiplied by T multiplied by S GP 0 of S divided by S and then we're going to write this term negative delta multiplied by T multiplied by S. So we just plug in what's GP of S divided by S in this expression and we separated each one of these, or we put each one of these multiplied by each other. Okay. What is this going to equal to? G of Z is going to equal to 1 minus Z to negative 1, and this is the Z transform of E to negative K T multiplied by S GP 0 of S divided by S E to negative delta T S, and I'm going to take the star transform, replace E to ST, where Z replacing E to ST with Z. Again, anytime I calculate the z transform of an expression of s, z transform of this expression is going to equal to the star transform with e to st replaced by z. Okay, now we use the fact that if I have e to negative k multiplied by s star, what is this equal to? I can take e to negative k ts outside. This is going to equal e to negative k ts and then star. Anybody remembers where we've seen this? We've seen this when we looked at the two properties that we use. 1 minus e to negative ts multiplied by an expression. We can take 1 minus t e to st. Okay, so therefore we can write g of z as equal to 1 minus z to negative 1 e to negative k multiplied by t multiplied by s, and then z transform of gp 0 of s divided by s e to negative delta ts. This is star e to st equal to z. And this we can express as g of z equal to 1 minus z to negative 1. If I replace e to st with z, this is going to give me z to negative k, and then the z transform of this expression is the modified z transform g 0 of z comma m, where m is equal to 1 minus delta, where g0 of z comma m is equal to gp 0 of s divided by s e to negative delta t multiplied by s star. M is equal to 1 minus delta and e to st is equal to z. And this is the modified z transform of gp 0 of s over s. Okay. Okay, let's look at an example. So as an example, we want to calculate g of z, 0 Alder-Hold equivalent discrete time model of the following system. And the system is u of k. We have a digital to analog converter. We have u bar of t. We have gp of s. We have y of t. And then we have digital analog to digital converter. And then we have y of k. So far, this is similar to what we've done. We want to calculate g of z equal to y of z divided by u of z. Now, we are given that gp of s is different than what we have been seeing so far. gp of s is equal to gp0 of s e to negative t multiplied t delay multiplied by s, and it is given by 1 over s plus natural log of 2 e to negative 1.5 multiplied by s. So this GP of s is given by this expression here. How is this different than what we've been seeing? There is now this delay element here, and we are given that t is equal to 1 second. We're sampling every 1 second. And what we want to calculate is we want to calculate g of z that relates y of k to u of k. And to do that, what we're going to do is we're going to come at the delay, and we're going to try to express the delay as k multiplied by t plus delta multiplied by t. This is integer, this is fraction. Now if t delay is equal to 1.5, and if t is equal to 1, then I can write this as 1 plus point, well, let me write it as 1 multiplied by 1 plus 0.5 multiplied by 1. And therefore, k is 1.5 is equal to 1 plus 0.5. Therefore, k is equal to 1 and delta is equal to 1/2, and t we said is equal to 1. Okay, so therefore g of z is gonna equal to 1 minus z to negative 1 multiplied by z to negative k multiplied by g0 of z comma m, where m is equal to 1 minus delta. And this g0 of m is the modified z transform. So in this case, gp0 of s divided by s is equal to gp0 is with no delay. So if I'm going to take the term of the transfer function without the delay. So s multiplied by s plus natural log of 2. This is the transfer function. Now what I'm going to do, we're going to use the calculus of residues. We're going to express this as c0 divided by s plus c1 divided by s plus natural log of 2. We're going to calculate c0 s multiplied by 1 over s plus natural log of 2 when s is equal to 0 and this is going to equal to 1 over natural log of 2. c1 is going to equal to s plus natural log of 2 multiplied by 1 over s plus natural log of 2 when s is equal to negative natural log of 2, and this is going to give me negative natural log of 2. So therefore, I have two residues. This is the first residue, this is the second residue. So this is, so just let me put them here in a table. I have C0 equal to 1 over natural log of 2 associated with lambda equal to 0. Here this is the root here, the pole here is 0. And then I have C1 equal to negative natural log of 2. Oh, sorry, negative 1 over natural log of 2. I made a mistake here. Negative 1 over natural log of 2. Negative 1 over natural log of 2. And this is associated with lambda equal to negative natural log of 2. Again, this is the where we got the lambda. This is plus 0. This is the second lambda. Lambda equals 0. Lambda equal to negative natural log of 2. C1, C0. Okay, so therefore, we can go to the expression of G0 of Z comma M. This is going to equal to z negative 1 of c0 e to m multiplied by lambda 0 multiplied by t divided 1 minus z to negative 1 e to t multiplied by lambda 0 plus c1 e to m multiplied by lambda 1 multiplied by t over 1 minus z to negative 1 e to t e to lambda 1, where m is equal 1 minus delta, which is equal to 1/2. So therefore, and of course this z to negative 1 is coming from the fact that k is equal to 1. K is equal, this k is this k. I don't want anybody to get confused. This is k is this k here. Okay, so therefore, if I plug in these values, I'm gonna get z to negative 1 multiplied by c naught that we calculated, which is 1 over natural log of 2 multiplied by e to m, which is 1/2, multiplied by lambda 0, which is 0, multiplied by t, which is 1, divided by 1 minus z to negative 1 e to t, which is 1, multiplied by 0, plus c1, which is negative 1 divided by natural log of 2 e to m, which is 1/2, lambda, which is negative natural log of 2 multiplied by 1 divided by 1 minus z to negative 1 e to 1 e to lambda 1, which is negative natural log of 2. And therefore we can write this as equal to 1 over natural log of 2 divided by z minus 1 minus 1 divided by natural log of 2 square root of 1/2 divided by z minus 1/2. Okay, so this is e with the natural log is gonna give me and multiplied by 1/2 is gonna give me the square root of 1/2. Does that make sense? E to negative natural log of 2, this is gonna give me 1/2, and then I have a square 1/2 here is gonna give me the square root. Okay. Now that we calculated, we calculated g0 of z comma m, we can find the pulse transfer function. G of z is gonna equal to 1 minus z to negative 1 z to negative k g0 of z comma m, and therefore if I plug in these values with what we calculated, 1 minus z to negative 1 z to negative 1 multiplied by 1 over natural log of 2 multiplied by 1 over z minus 1 minus square root of 2 over 2 over z minus 1/2 So this is square root of 2 over 2 is the same as 1 over square root of 2. Okay, I can simplify this. This is 1 over natural log of 2. I can write 1 minus z to negative 1 as z minus 1 over z, and then I have another z. This is z to negative 1 will go to the denominator, becomes z squared, and then I'm gonna have z minus 1/2 minus square root of 2 over 2 z minus 1 divided by z minus 1 multiplied by z minus 1/2. I can cancel this with this, and this will simplify to 1 over natural log of 2, and then I'm gonna have z multiplied by 1 minus square root of 2 over 2 plus square root of 2 over 2 minus 1. So just rearranging the terms in the numerator, and then I have z squared multiplied by z minus 1/2. So this is the results that we're seeking. I know it's lots of calculations and lots of room to make mistakes, but the more important is to understand the derivation and being able to apply to calculate the pulse transfer function for a system that has a delay. Okay, now one thing that I want to mention here before I wrap up is that this shows you the advantage of the digital controller versus the continuous control. If this system has a delay, the system that we considered in this example, when it has a delay, if I were to study this in the continuous time domain, then this delay will result an infinite number of poles of the system. This delay, I can expand it using Taylor series, is going to result an infinite number of poles in the continuous time domain. However, in the discrete time domain, I have a finite number of poles. I only have 3 poles for this system, which makes it easier to design a digital controller versus an analog controller. Thank you, everybody.